Hello everyone, welcome to Engineers Ireland. Today we're starting calculus, and you always start calculus by looking at differential calculus. You normally would call it differentiation. This has been left well on into the course of these talks because calculus, it's like putting a roof on a house. You need to have the walls up before you put your roof on. The foundation, well, there are two sets of foundations from mathematics. You've got algebra and geometry, and what I would hope that you can recognize now at this stage is that both of those have not only crept in, but they've been actually central in everything else you've been doing since that. Now we're bringing you to a point where the type of maths you do will start to look very different to the previous stuff. Anytime you come across that in mathematics, you should just say to yourself that the language is changing. In the same way as when you started looking at trigonometry, when you get sines, coses, tans, secs, etc., and all those kind of things, you just recognize it's a change of language. We know now that tan theta is related to a straight line. Is basically just the slope of the straight line. You will now find through differential calculus that the dy dx has only got to do with slopes. If you differentiate a second time, you get the slope of a slope, which is curvature. And if you were asked to do it a third time, you'd be looking at kurtosis, but of course that's not on your course. That's something for you to find out next year when you're in college. So then, why differentiation? What's special about differentiation? Let's start back with geometry of the line. Once you write the equation of a straight line in the form of a single y equal to so much x's and a constant, we know that the constant is where it intercepts the y-axis and the slope is m. That was all well and good while people were just working with a straight line. But when you had a curve, things changed. Now, just picking 2 points off, like we could have up here, finding the difference in the two x's, which you can either call delta x or you could call it h. I don't care which one of these two you use, whether delta x or h. I personally prefer delta x's because you can actually see how that then very quickly becomes, first letter for delta is d, so you know your dx, and this one here, delta y, the change in the y. And we know that m is the difference in the y's divided by the difference in the x's, and that really is dy dx, which is what you're about to find out. What did scientists and mathematicians do in the old days when they had to get the slope of a curve? We'll say, for argument's sake, there. What did they do? Well, generally what they'd have done is worked out the values of the curve for a few points to the left and to the right of it, plotted up, and estimate as well as they could from a good accurate plot what the slope was. That's just an estimate. An estimate is grand in many cases. For example, as an engineer, I'm quite happy to estimate things. The only important thing is, once I've estimated, I then have to work out what sort of tolerance do I have around that estimate with inside which the real number would be. For a mathematician, that thinking doesn't work at all. Mathematics has to do with being exact, and it's particularly important in the field of mathematics that the rigor of mathematics leading to exact proof and definition is held to, because you may think meaningless simplification can have serious consequences. But I'm fortunate. As an engineer, I simply have to be accurate, sufficient to the task. So mathematicians a few hundred years ago had a problem. The problem was they could get a reasonable estimate. It took a fair bit of time, but they couldn't be exact. Now along comes two guys, Newton, and he was working obviously in the UK, and a German who didn't really get sufficient credit for quite a length of time, Leibniz. These guys had a very simple idea. Fundamentally how it works is we're saying we're interested in this point here, this location. For this given x, I know the value y is equal to the function of x. So I know the actual coordinates of the point, but I'm trying to find the slope there. Now if we go back up to this first setup again, this one here in the line, because the line is straight, we don't care what 2 points we pick, and neither is more important than the other because it's the same slope all the way through. In this problem we're looking at now, there is a difference. Once I pick a second point, the only reason I would even think of picking a second point, such as, for argument's sake, a point here, is because I'm looking for the slope of the function at xy, this point down here. That's what I actually want. So this one is the most important one. Now, because it's the most important, we really talk in terms of it, and even when we look at the second point, we're talking about basically how far away it is from the first one. The second point, we'll say, is a distance away. Which you can call x plus h. And we're saying, now this is where I'm going to have to change my line a little. We're saying that distance here, I know it. It's x plus delta x minus x, which is delta x. And written in the other fashion, so we know the difference between them. This second point, the one on the right, it's a bit like having two numbers 5 and 7. While they're equally important, you can call one 5 and the other 7. If 5 is the important one, the one you're focusing on, you're better off to think of 7 as 5 plus 2. And that's what we're doing here. The one on the right is our first one plus a bit, and we get results from this. We can look at the differences of the two y's here, and we can say that it's the value of the function when we put in a value of x plus delta x into it, minus the value of the function when we put in an x. We can use the same equation now as we have used for many years for finding the slope of a straight line, because we're now looking at the slope between 2 points, which is all we've been doing for years, and we're saying this should be an estimate, or we're looking to have this as an estimate for the slope down here. What do we get? That's equivalent to what we've been doing for years. Well, what what happens? We know something. We know we've actually got the slope between these 2 points here, which is the slope of that straight line through the 2 points. Your question is clearly, at this stage, is that the same as the slope of the curve down here? Which I'm pretending is this blue line because it's near as I could get to a tangent to the curve that we're dealing with. And you can clearly see that the red line doesn't have the same slope as the blue tangent to the point xy. Many people, I'm sure, got this first step of differentiation, and they probably even realized that if I actually had picked a second point, the one to the right, closer to the one I'm interested in, that I'd get a better estimate. And they may have even gone to great lengths to get in quite close. But the real trick here is the second step in the thinking. The second step is, well, even if I brought those in closer, and if I set up a new graph, and we're still looking for this guy, and we're going to pick a second point which is way closer, slightly exaggerated, but that red line still doesn't have the same slope as the blue one. However, it is an improvement on the one above it. What these guys realized is, in this second case here, the delta x, which is what you can also call h, is smaller than the delta x up here in this drawing here. And now that it's smaller, we've actually got a better slope, a better approximation to the actual slope of the tangent at xy of the function. So we can say just add one little bit of information up here. So we're saying delta y over delta x. As a basic rule of how we talk and write our mathematics, we use these deltas when we're actually talking about some very small piece that actually really does exist. It could be exceedingly small, but it's still there. We write this d, which is the first letter of delta, when we are saying that the limit of this process, as I get my delta x's or my h smaller and smaller, that could have been h goes to 0 instead of delta x. What we're saying is the actual limiting condition of this, in other words, where delta x is so small that you'd be just as well to say that it's 0. However, it's not 0. It's so small it could well be 0. In that limiting condition, we've got the dy dx with the d rather than delta. Now what you have to be able to see here is all we've really done is played around with the slope equation for a straight line. That means that dy dx has just got to do with the slope of some function. Now the second thing you need to know about these things is that what we're referring to here is first principles. And there's 6 functions asked by first principles. Any one of the 6 can come up on the Leaving Cert. Once we pass those, you're now into differentiating by rule. And fundamentally, the difference here is as distinct as the difference between being a chef and being a cook. A chef has to deal with something right from the basic ingredients and develop up a particular, we'll say, course for a dinner or whatever. A cook follows a recipe. Most of what we talk about in these chapters, and we call calculus, differential calculus, most of that is the work of a cook. It's easy. You will find as we get through the 2 or 3 classes we'll have on this, that you're following rules. The rules are also in the logbooks. It's easy to teach someone to follow rules. This piece here, this is the heart of what differential calculus is about. And what you will no doubt find out in the years to come when you're in college is that anytime you come across something that's quite new, it may have to do with, we'll say, stresses in a small unit of volume inside a huge oil-bearing rock, we'll say for argument's sake. If you're looking at the stresses involved in that, you'll go down to a little unit size and you will start from first principles and build and develop stuff. This stuff here really is where it all started. Out of interest, Newton was ridiculed over this by an Irishman, a Dublin man actually, Bishop Berkeley, who very successfully ridiculed him. You'll see the reason for it once we take one example, a very simple example. This is one of the 6. It's the easiest one. The x cubed is another one. Very easy to work out the x cubed one also, and it's generally in the books. So let's look at these, the easiest one, so as we get the idea. And then I will explain to you why the other 4, the remaining 4, why they have to be done slightly differently from these 2, but that all know the concepts remain the same. We want to see what's the basic central idea here, and we'll do it by example. So f of x is this. That implies that the f at x plus delta x is equal to x plus delta x squared. And we know that's equal to x squared plus 2 delta x's by x plus a delta x squared. You may not like the delta x's. I use them because they clearly tie into these. It's interesting. Past Leaving Cert math students have to use the delta x. I don't know why honours have to use the h. We're now in a position to be able to fill out our equation. So first off, you always start by writing as I said, you can use h here if you choose. So we're now populating out our equation. So we're saying in this case here we've got that, which we got over here, minus this one, which we know here. So it's this thing minus that thing, and divided by the delta x. So we'll say it's equal to the limit as delta x goes to 0. And we can see that that cancels that. And the other 2 terms, the ones that are left at the top, they all have a delta x in it, okay? Which will allow us, and I might as well do it in the one jump because I'm running short of space here, it'll allow us say it's the limit of 2x plus delta x. as delta x goes to 0, as this guy gets down to 0, there's no change here because that's 2x, and x is not delta x. But this guy, actually, he approaches 0. So we can say that the answer is 2x. In the limit, in the final analysis, we can say that the slope of y, this function of x, which is x squared, we've got a slope of 2x. So when x is 1, we can say that the value of the function is 1 squared, which is 1. If we look for the slope, it's going to be 2 by 1, so we'll have a slope of 2. When x is 10, y is 10 squared, which is 100, and the slope then is 2 by 10, which is 20. Why was it that Bishop Berkeley was able to ridicule a man of such immense stature as Newton? It all comes down to going from, we'll say, this line down along here across to here. In this line, delta x must have a value. It can't be 0, because otherwise we've something divided by 0. So it's something other than 0. It's more than it, okay? Down here, we're now saying in the limit, this delta x actually goes to 0. And over here, it's so small we say it might as well be called 0. Berkeley didn't like the idea of that. Something either exists or it doesn't exist. The analysis, I suppose, interfered with his sense of order of things. Something is either true or it's false. It either exists or it doesn't exist. You can't have it existing here and not existing down here. And it took, I believe it was right into the 1990s for pure mathematicians to be able to come up with a methodology and rigorous mathematics to finally lay to rest this problem. So what happened in the few hundred years in between? Well, all good engineers and good scientists and practical mathematicians used calculus because it worked. Not knowing a rigorous proof to allow it be accepted by pure mathematicians didn't interfere with us. It's been used because this is one of the most powerful things that you can learn in mathematics. It's a gateway into a totally different plane of maths. You'll be surprised, and as a matter of fact, once you finish your Leaving Cert, you could head off down to Eason's or Hodges Figgis, which is a very good bookstore, and others, of course, and you can get books on, I suppose, entertaining calculus. You will be entertained with the kind of problems that they have, and you'll be very surprised with how many of them you can actually come to terms and actually find a solution. This is a lot of talk, having only gone a few little pages into this chapter, but it's worth it because this is the golden key of calculus. The chapters, in fact, start by discussing limits. I'm asking you now to, rather than starting looking at limits in this chapter, I'm asking you to go back to the chapter on sequences and series, because you get introduced to limits there. There's a lot more of them in there, and you'll get the understanding you need, and you'll get the little rules and conditions that make working out limits easier. You'll get them in that chapter. There's very little extra by way of limits in the calculus chapter. They're useful, but they are quite easy. Now, I may at a later stage do one full talk taking into account the limits that are in the series and sequences, in calculus, and in the special question, and just put it all together. But at the moment, there really isn't much that should hold you back from just going through the little bit of limits that's in this. With that said, we're now saying that there are 6 of these items that we're supposed to work out. You've seen the first one, which is very easy. X cubed is done almost the same way. You've got 1 over x, you've got root x, and the last 2 are trigonometric. We play a little game with these, and we do so because they all share one common thing, which is the only little hurdle you have to get over in whatever problem you're given in working out differentiation by first principles. And we'll examine it by picking the easiest of the 4, which is the 1 over x. Now we know how to populate out our function for working out differentiation. I'll run across the page in order to save myself a little bit of space here. Okay, what's the problem? It's not much of a problem in this one, but you will understand it. The x, the delta x here, is trapped along with an x inside an expression. In this case it's 1 over x plus delta x. What we've got to do is get this delta x released so that we can have this guy over here neutralize that guy here. It's pretty obvious how we do this. We have 2 fractions above the line, and we'll just unite them. Is that correct? Remember, most marks are lost not by the pieces that you can't clearly remember in theory. They're lost by making silly mistakes, particularly relating to signs and little easy bits like this. As it turns out, we are happy enough here. What you can see now is that guy was able to cancel that guy. And that's the problem that we discussed over here. It's trapped in here, and we want to release it so as we can get them to disappear each other. So what we now have that cancels that. what happens now? Now we're going to do the bit that Bishop Berkeley didn't like. As delta x goes to 0, we're saying this guy is going to 0. In the limiting condition of that progression, we can state that we now have x by x underneath the line. Now that's easy. But the important trick is knowing that we have to separate out two things. We have to get this x out from underneath there so as we can deal with that x over here. You'll also notice that I've been bringing the whole function all the way down along with me. That's a bit wasteful. So when we now look at this one, the root x, and you'll see again how we bring in a little trick so as to separate out the x so as we can deal with it. What you will find is we will now go through this in a simpler way where we don't carry the whole equation with us. We've got the exact same problem again. These two are trapped together underneath the square root sign. We want to be able to release this piece so as he can deal with that piece, or vice versa. What do we do? Well, you do know we can multiply anything by 1 without changing it. And while we can say 7 by 1 is 7, there isn't much use in saying that because we're just going around in a circle. The form of 1 that's useful is something divided by itself so long as the thing isn't 0. So we're saying what will work here, what will help us here. What you have to understand now is we're just looking at something you've been looking at for quite a length of time. We're looking at one of the factors of the difference of squares. It's very powerful, and I keep reminding you of this particular thing because the more I remind you, the more likely you're to keep this in your mind when you're in the Leaving Cert, because it's a very useful means of solving problems in the same way as we'll say in algebraic questions when you've got an inequality to prove some sort of an inequality. You start hunting for squares because perfect squares imply that the result of them is going to be positive, and that's a useful enough thing. Here we have a classic example because these two conjugate factors. You've got a pair here and its conjugate here. We're looking at one of them up here. What we'll do now to release the x from underneath the square root is we'll multiply in by the conjugate of this. But we can't multiply 7 by 3 and still expect the answer to be 7. So as well as multiplying by the conjugate, we'll also divide by the conjugate. Now we'll multiply by 1. Now above the line you don't need to do any multiplication because we know when we've got something minus something multiplied by the first thing plus the second thing, all that happens is we finish up with the first one minus the second one, and the powers have been doubled. So straight off you can say this is equal to x plus delta x minus x divided by the conjugate. There. Still haven't got used to this thing. See? We've now managed to release this so that it can neutralize with that. Now we can go back to the whole equation. And all that got divided by delta x. And the nice thing is that kills that. So we will write out the next line now. It's the limit as delta x goes to 0 of 1 all over as delta x approaches 0. Remember, to be kosher in mathematics here, delta x won't be 0. But it'll get so close it'll make no difference at all. We're saying as this goes to 0, then clearly that's going to 0. So we'll say that is equal to 1 over root x plus root x. Okay? Remember, the secret is the same in this one as in the 1 over x one. We have to find a way of releasing this to deal with this. There's just two left. The first one you'll normally find in the books, the sine one, and it's quite straightforward, but you have to be very careful with the cos one. First off, it's not in many of the books, and certainly you're liable to make a mistake when you do it, and the reason for it is just one of how you look at things, and I'll explain that when we get to it. But just we'll do the first half of the sine one, and we'll just bring it down to where the rest is obvious, and we'll leave it. Okay. Y is now going to be this function of x, which is sine of x. So when we've got x plus delta x, that implies the sine of x plus delta x. So when we've got x, we got sine x. When we've got x plus delta x, we got sine of x plus delta x. We'll start by saying that implies the function at x plus delta x minus the function at x is going to now be equal to the sine of x plus delta x minus the sine of x. All okay so far. Same problem. That's stuck inside that sine, so it can't actually deal with this guy. What we have to do is to come up with the trick to solve that. What you will notice in your logs are a set of 4 trigonometric functions, and the nice thing is they're all happily there. And what we want to find is something that will allow us break this thing up, and we're looking here at a sine minus a sine. So when you look down through these, you do actually find it. And what you find is sine of A plus B. You'll find that guy. And you're told that it's 2 cos A sine A B. Now then, how do we proceed? That's a B. You can go along and memorize what the two things should be. There's no need to worry much about it, because down here on the right hand side we can actually do two little simultaneous equations that'll work out what the A is and what the B is. What do we know here? We know that this first one, this thing in here, is A plus B. You can call that equation 1 if you want. We know that this second one is A minus B. And we can recognize very quickly that if we just add these two equations, we'll get ourselves a nice little result. Is this okay? Are we better to add, or are we better to take one away from the other? What do you think? Well, it actually makes little difference. Let's look here. We'll add them first, and then we'll take them away the next time. I prefer to leave it looking like this. That's 1 plus 2. We could have taken one from the other, and then you'll get 2b is going to be, the x's will cancel now. We're going to be taking the second equation from the first equation. So now we know what will populate that location and that location. Now then, what's the next step? From limits, you will find that there's one trigonometric trick in limits, and it's that the limit, as theta goes to 0, of sine theta divided by theta is 1. Here's a sine. So we can in our mind consider h over 2 as the theta, and we're saying, when I now get to the next step here, which is bringing in the full equation with the limit on it, I'll want to be able to disappear out this guy, and I can only do it if it's going to get divided by the angle that it's the sine of. So it has to get divided by h over 2. If we go back to 7 again, the number we were talking about earlier, I cannot divide 7 by 2 without changing it, unless I simultaneously multiply it by 2. So here again we're going to bring in the trick of multiplying the equation by 1 and therefore not change it, in the form of the useful thing divided by the useful thing. See the h over 2 being multiplied above the line and below the line. I've actually got what I want here now. What else do I know? Well, that little 2 here is going to cancel that 2. So this is now equal to cos by and now we go to the full equation. So I just realized I've actually mixed things. I'm using h's now instead of delta x's. Allow me change this, please, and do accept my apologies over this. I'm so used to working in both. That's a delta x, that's a delta x. Sorry about that. Delta x. That's kind of embarrassing. That's starting to look a little ratty, so what I'll do is I'll rewrite it up here. This delta x is going to cancel this one. A rule of logs, or sorry, of limits, is that the limit of a function by another multiplied by another function is the limit of the first function by the limit of the second function. So I can actually now bring that into this. This is the special trigonometric limit, and it goes to 1. As delta x goes to 0, we're saying that's going to 0. So it's equal to cos of x. This little bit that I have over here on the right hand side, you don't have to do that. I'm just showing you that if you've forgotten that what should populate out the equation when we bring in this trigonometric identity, you can go back to stuff you've been doing since second year, which is set up 2 simultaneous equations and solve. It isn't a reason for you to stop on this question. It may be a reason for you to spend 2 minutes, which isn't a sin in the Leaving Cert, especially when you get down to knowing your two correct answers, namely that and that. That's the sine one. The last one of these is the cos one, and this is the one you have to be careful about. Oops. Where's our problem? Let's start plowing our way through this. It's taking the next step that's going to that is the little problem with this one that you didn't have with the sine one. Again, I'm just asking you to go to your logs and look at the 4 equations, the ones that tells you how to, if you've got the cos of something plus the cos of another thing, the sine of something plus the sine of another, the cos sine, sine cos, blah blah, one of them looks different to the other ones. I'll just write them for you. If I'll do that, I'll give ourselves more space, and I'll get rid of this in a minute. Let's look at the 4. One of those, as they used to say in Sesame Street, doesn't look quite like the others, and it's something that's very easily missed. See this first term here? That's an a plus b. That's an a plus b, and the last one is an a plus b. It's awful easy for your eyes looking at these 4 equations to make the mistake, and the mistake is this is an odd one out, this equation. It's an odd one out because you have the a minus b first. Watch over here. The a minus b is there, the a minus b is there, the a minus b is there, but the a plus b is here. The way out of this is to, just as you start on this differential calculus problem, you can say to yourself, okay, I have got a cos of an a plus b, and I've got this guy. This is clearly bigger because there's an extra bit in it at delta x. So what we're going to do is we're going to convert our equation into minus outside of that's the important minus. Now it'll look exactly the same as those two equations and that equation. It'll make it easy for you because you have it in the same order as this one. Now we could do it that way, or you could have said the alternative, one or the other. Okay, the alternative is you could have said that that is equal to minus outside of cos x minus. And then you could use the equation as you see it here. Remember, if you're asked the cos one, this is the likely place you're to go a cropper, because after that you have exactly the same stuff as you had in the sine one. What we'll finish up with is that it's now going to be equal to minus 2 sine of that bit is the same as before. We're going to cure it by using the limit as theta goes to 0 of sine theta over theta being equal to 1. We'll cure it the same way as we did in the sine, using that trick. The one fundamental difference is what you will notice is we're carrying a sine out here, whereas when we were dealing with the differentiating the sine function, we had a cos out here. The game plays identically the same from here on in. The odd thing is something this simple as rewriting that side into this, or rewriting this into that to turn it into looking like this. That's where you get your minus. If you don't do that, you will finish up when you get down to the end of the overall thing, and you'll find that the differentiating cos will give you sine, which is untrue. This is a very silly thing, but this cos one comes up quite a bit, probably because people don't see that. They're the 6. So, can you dismiss differentiation by first principles now? Well, no you can't, because it comes into quite a number of other things. And the bit that I particularly like, well, there are a few parts to this chapter that are, childishly simple. There's the proof that the d dx of a constant by a function is the constant by the d dx of a function. And then there's the proof that the d dx of two functions is equal to the d dx of u. That's done by first principles, and it is childishly simple. We're not going to go through it. We're going to go and look at the proof of the product rule, because it's first principles proof. What is the product rule? Now, by the way, I haven't dealt with those first 6. We've technically moved into the being a cook, not a chef, into recipes. And we'll get on to the rest of the recipes. But let's just look at this piece because it is a first principles proof. What we're saying is if I wanted to differentiate a product, u by v, where u is a function of x and v is a function of x, we want to be able to prove that it's equal to u we're left to prove it using first principles. And there is a really cute trick that comes in here. it's another one of my favorite things in maths, and that is it's how adding nothing to an equation can allow you proceed. And if you hadn't added nothing to it, you wouldn't be able to proceed. I've mentioned before, when we were dealing with geometry of the line, there's a beautiful example there. There's also a lovely example in geometry of the circle, where adding zeros make big differences. This is the one in the calculus for the Leaving Cert. What do we know? Well, we can start off in the usual kind of fashion and say, it's the ddx of uv is equal to the limit as delta x goes to 0 and we can happily populate this out because we know these two little functions here. It in a fashion that won't confuse us. We're just populating the thing out. Where do you go from there? Well, not very far, unless you add nothing to it. In the same way as multiplying by 1 is very useful when it's in the form of the interesting thing divided by the interesting thing, we can add 0 in the form of an interesting thing minus the interesting thing, and obviously we can put the minus version of it first, and that's what we'll do here. So how can we know, if we can't remember, how can we actually get through and solve this, which comes up quite a lot actually? Well, the trick is to focus on this, the second one, and we'll say to ourselves, okay, and I'll write it over here because it's up beside it, saying that's going to be the v of x by the ddx of u, and we're saying I know what the ddx of u is. Isn't it the limit as delta x goes to 0? And we'll say it's u We know that, don't we? We can now play it around a little bit because there's no delta x with inside this v part. I can multiply it in. Clearly, that term is the same as what I have here, and the new bit is actually what I'm going to hunt for. I'm saying if this was only in the equation down here, I'd be able to now start to separate out this total function. I'd be able to separate it out into the two bits. That allows me finish up with those two bits. See, they're only separated by a plus. They're separate. So if I add something in, 7 plus 2 is not 7, but 7 plus 2 minus 2 is 7. So we're going to add in this bit over here, and then we'll also take it away, just to ensure that we're not going to break our equation. So we'll say this is equal to the limit as delta x goes to 0 and now we'll go u of x plus delta x And we'll go to the very back now. And we'll add in what we need. We'll add in this thing. Because we've added it in, 7 plus 2 is not 7. We must now also take it away. What we've succeeded in doing is adding nothing. So we haven't changed anything. But in adding nothing, we've brought about a huge transformation to the equation, because we can split it in a useful way. So we can say this is equal to the limit as delta x goes to 0, and now we're going to split the whole thing. We already know that this guy can get pulled out here. So that lower part now is going to be, or this second part is plus, oops, I haven't talked about pulling it out, I didn't proceed by not doing so. And in the first one, do we have a common term? Clearly, this guy is common. I can pull it out in its own separate limit. When delta x goes to 0, that goes to 0, and I'm only left with u of x. It is multiplying into this second one. And what do I have here? That is the first principle's definition of dv dx. And over here I have plus v du dx. It's a beautiful thing to think that this proof is dependent on adding nothing. And as I said to you, the secret to it is to focus on the second one here. Work out what it is. It's all of this. Recognize that we can multiply that in here. We get that. We say, I have a term in here that I didn't see in my main equation, so I'll add it in, and I also must take it away. Well, you'll probably have to get to be as old as me before you find that that's very interesting and very elegant. But there's no denying my belief that it is. We've basically looked at the important points in relation to first principles. What we can do very quickly now is cover the more basic parts of differentiation by rule, which is you being a chef. First off, they're in the logbooks. The old logbooks were more complete for calculus than the new logbooks. So let's write out 6 that I expect you guys to learn off the glán bheabhair, in other words, off by heart. And they're the 6 that don't show up in the new logbooks. We'll have some function, and we'll say the dx of that function. And by the way, that's the shorthand way of writing it. So what are the 6 functions? If I differentiated sec, cosec, and cot, what do I get? Learn those off. The next 3 are the inverse trigs of the same ones. I'll write this one further down. What's the basic difference? All of this you can see here. So 1 is the minus. That's the important bit to remember here in this one. If you remember these 6, and by the way, don't feel all upset that you have 6 things to learn. Students, certainly all the way up to 2 years ago, had a mass of equations that you had to learn for mathematics for the Leaving Cert. Now, with the new logbooks, you don't have to. But these 6 are very important. You will find that there are equivalent ones in the integration that I will want you to learn, but you're looking at no more than 12 things, and they'll make life easy for you, and I'll explain that in a few minutes. We've looked at the product rule. We know how to deal with products now at this stage. The rules of it, I'm sure you're familiar with, and you should be familiar with the practice of it. So there isn't too much other than to say in dealing with the product rule, than to provide one example. After that, you should understand the principle anyway. we're saying is a complicated thing like this has been simplified into two much easier bits, these. That is definitely a bargain, to go from this thing to this simple problem. It is a powerful tool. There are many cases, though, where it isn't a product, but you've got a quotient. And the next rule, obviously, is going to deal with those. Y equal to U over V. Derivation to this is very straightforward. It would be very much a waste of your time for me to go through this with you, because you can easily look at this in the book. It's straightforward. It's not like the derivation of the product rule, which did require explanation. The only important thing to remember now is be very careful, because okay, the u is on top here, but it's the v du dx comes first. Okay, that's the one thing. It isn't u dv dx minus v du dx. Okay, obviously the easy thing is, if you haven't learnt it off absolutely by heart, is to have the logbook open beside you and religiously write it down as v du dx minus u dv dx all over v squared. Right then, why is it that I mentioned to you before to learn off 6 differential identities, the sec, the cosec, and the cot, and similarly the inverse trigs of them? Well, you can easily get, for example, needless to say, this is going to be a silly one to begin with. That's clearly in the territory of u over v. But we know what 1 over cos theta is, don't we? It's sec theta. So we can say that implies y is tan theta by sec theta. And now this is clearly in the territory of u multiplied by v, which is obviously a quicker calculation to do. If only you remember what the ddx of sec is. In general, and the reason why I've asked you to learn those 6 off, is when you're faced with a quotient like that, you can convert it in many cases into a product and then just use the product rule. The next rule that you have is the chain rule. This is very powerful, and it'll seem very stupid to you, but I always think of it by way of this little drawing here. There's no real marks for guessing that that's an onion. So, when you think of chain rule, why should you think of an onion? Well, differentiation, as powerful and all as it is, can really only operate through one layer. In other words, I can get the d dx of cos x, but I'm in real trouble if I have the d dx of cos of something else inside here. It could be an x squared, it could be any sort of function inside here. This I can't do, not with straightforward differentiation. We need a chain rule. That's why I show this onion here. You actually only can differentiate the outside layer. It would be very nice to think that you had a method of differentiating that, this one, and all the way in as far in as you need to go, and that there'd be a means of, in doing all those, simple one step. This is a one-step function. X is only stepped one. It's one layer of an onion in. It'd be nice if we could do a series of one-step differentiations to give us the result of a complicated thing like that. And that's where the chain rule comes in. The d dx of y. Well, it'll come as no major surprise to you that I can multiply it by 1 and it won't change it, and I can multiply it by 1 again and it won't change it, and 1 again and it won't change it. And you'll notice we're back into the lovely little game again of finding multiplying things by 1 is very useful. 1 in terms of something useful divided by itself. We'll just say that the first useful thing was dr. The next one, you can call them anything. It could be d apple for all I care. And on and on and on. You can do as many of these as you like. Obviously, for the Leaving Cert, there's a limit to them. There's maybe 3 or 4 you might have to do. But there's no reason to think that this can't go on 20, 30 or 40 times if that's what's required. Now, you would live and pray that you don't have to go 40 layers deep into an onion like this thing. But let's look at it. What do we have to do now to turn multiplying by 1 and multiplying by 1 into something useful? All you've got to do is to take this guy, push it over here, and say, isn't that equal to the dy dr by dr? See, they all have got pushed over now. And even though this is still 1 and this is still 1, we've actually found a method for solving problems like this guy over here. Watch how we do it. So we can, in our mind, look at this guy and give it a name. You don't have to write it on paper, but in our mind we could call that r, because we're using r. We're saying, I can't get the d dx of cos r, but I can certainly get the d dr of cos r. So we'll say that is equal to the d dr of cos r is minus sine r. So we're saying, okay, that's the d, and what were we calling r? It was the x squared. Now, nobody asked for the d dx squared, so you have to bring it up here. And this I can do, because there's only one layer to this onion. X is just in one step. In this case, it's the inside the square. And we can say that that is now equal to minus sine of x squared by 2x. The chapter runs on and it talks about more complicated equations, and we'll just look at one of them because they're all basically the same sort of thing. And once they talk about more complicated ones, you can basically for that read things like it's a chain rule. It doesn't mean it's only a chain rule. You may use a chain rule followed by a quotient rule or followed by a product rule. but fundamentally the secret to all of these ones that sit many layers deep is to use the chain rule. One that's already worked out here in the book is probably the best one to do for me anyway. Okay, how do we interpret that? If, by way of the onion that we talked about earlier, we look at the layers of it and we'll say, I do have sine of 2x squared plus 1, and all of that is inside the most outside layer, which is it's inside the cube. So technically in our mind I could let all of that equal to the r thing, so that we will have a dr now. If I call that r, when I'm now dealing with dy dx, you can say, I can get the ddr of r cubed, can't I? Which is and having written this down here, I must write it up again above the line. And now we're looking at this guy. I can't get the sine of 2x squared plus 1 because the x is buried too deep. I can call this thing, though, I can give this a name. All of this can get a name. We could call that p for all we're talking about, and I can certainly get the ddp of sine p. So underneath the line I can write down and having written it underneath the line, I must write it above the line. And here the x is only one layer in, it's just inside a square. So we can do that one. At any time we only can differentiate one layer into the onion. In this one here, outside layer, next layer, next layer. So there's 3 layers to this guy. The ddr of r cubed, it's 3, whatever the r was. In this case it's sine of 2x squared plus 1 squared, so that's 3r squared in our mind. What was the p? We were talking about the ddp of sine p. That'll be cos. The next one over, it's the ddx of the p, and we will go this whole line. The nice news for you, this whole line here, all of that stuff, you don't need to write that. I'm only writing it here so as to show you that we're still just dealing with the d of our function dx, because the others cancel, and they're written out so that you can see how you step one layer deeper into the onion every time. Outside layer, next layer, next layer, and you can keep going and going, and you must keep going until you get to a point where the x is just buried one layer in this case inside a square. You could have gone straight from that to here once you understand the principle. So you'll get it's 12x outside of all the rest of the stuff. what's implicit differentiation? Well, it's where you really can't, you either don't know how the y relates to the x, you don't know the function that it's standing for, you just know some relationship. It could be an identity, but you don't necessarily know what the y means. What we are clear about is that the dx of y, we only can work that out when we know that y, or what it is in terms of x. So, example, that we can do. This thing up here we can't do. If we were asked not an idea. But we can bring in the chain rule. And you will notice these do cancel each other, so we're still dealing with the dy squared dx. And in this case we can say that's equal to 2y dy dx. And while we don't know what the dy dx is, we have a name for it at least now. We're calling it dy dx. It's something. And maybe there's another equation out there that will solve the problem for us, but at the moment we don't need to worry about it. The kind of things that we're given in this implicit stuff is 7x squared plus 2y squared minus 5xy cubed equals 8. We want to find dy dx. So we'll say it's equal to the d dx outside of all of that stuff. And now we can start working on it. First term, the d dx of this. How about this second term? We don't really know, but we can use what we did down here. It's a y squared thing. So we're going to get 4y dy dx. And now we're looking at this minus 5x y cubed. So we're looking at, we can bring out the constant, of course, and this guy, differentiate a constant, you get 0. Now we're left looking at this one. What do we have to do with it? The thing you have to remember is that's a product. There's an x multiplying into a y cubed here. Both of them are functions. So what we have here is the need to bring in a product rule. Here we differentiated this one. Have we left anything out here now? We can't differentiate y with respect to x unless we know what it is. Okay? Right? Now we want to differentiate this guy. So it is minus 5 d dx of x is just 1. Now we're happy. What's the last trick? We're going to round up all the usual suspects. Things that have got dy dx's in them. and now we divide across. Really, this is not hard. It's a little awkward. It's very important for you to not start a problem by saying it's hard. If you say that, and if you say it often enough, the mind will start to think things are hard. Something may be unfamiliar to you. That doesn't mean it's hard. The secret is, if you say it's unfamiliar, your mind will say, right, let's set about making this familiar, making sense out of this. And then you just follow your methodologies and your process. All we're doing here in implicit differentiation is good old-fashioned differentiation. Only when I come across a variable, in this case y, and I don't know how it relates to x, I don't know the function, I don't have something like this for it, I can still differentiate whatever the functions of y are in terms of y, and then I have to bring in this dy dx. It's all just related to the chain rule down here. Having done that, you gather up all of the dy dx's together, shove everything to the other side, and divide across. Now, there isn't much more left to this chapter, and all I intend to cover right now are the parametric section and the differentiation of inverse trigs. After that, the stuff that deals with logs of natural logs and that deals with the exponential function, I'm not going to deal with, because when we were looking at algebra, and also in the introductory talk, we actually went through in considerable detail how to deal with indices, and we also looked at how to deal with logs. And there's really no difference between these other than the natural log can be called ln. All the rules of logs are the same. The rules in relation to the exponential function, the e function, are exactly the same as any other base. I've often been surprised that they're actually involved in the differential chapters. They really should be over with all the other indices and logs. So there's only two more little bits, and this one again you'll find has only got one little trick in it. You'll find also the last section, the inverse trigs, there's only one trick in it. There is a cute game you can play also that'll make life easier for you, and we will certainly be showing you that when we're looking at the past questions, and we're within about 3 weeks of dealing with past questions. We've already come across parametric versions. We've come across them in geometry of the line and in geometry of the circle. You wouldn't necessarily have been told, but we've been doing it in complex numbers also, once we moved on into the polar form, which is what's the radial length and what's the rotation, what's the angle. When we were dealing with that, we were now firmly in the territory of a parametric version. So here now we're talking about a situation where x is known in terms of some other variable, and similarly y is known in terms of some other variable. What do we do about those? We can appeal to the chain rule again. Very useful, this chain rule thing. We want to find dy dx. But we know y in terms of t, and we know x in terms of t. Obviously, we could play the little games that we have in the previous places where we came across parametric versions of removing the parameter t to find y in terms of x. And while that's workable, it's slow. There's no need to do it. And the reason there's no need to do it is because there's two things we can do already. We can say, definitely, I can do dy dt. It's only a name change from dy dx. And I can also do dx dt. Those two I can get very readily. Now then, let's multiply by 1. And what would be the useful form of 1 that we could bring in? That version. dt divided by dt. It's only 1. We've got half of our problem solved now, because that's something I can easily do, see? But look at this half here. We know that if 1 over r equals 7, that r is 1 over 7. And likewise, if 1 over p is equal to 1 over 2, then p is 2. You can always flip things. What happens if we flip this particular guy here? What do we get out of it? We find this. If I had said to you, I'm thinking of a number 3, and if I flip it, find its reciprocal, I'm looking at 1 over 3. If I start off with a number 15 and say I want to divide 15 by 3, I can do it in two ways. I can say 15 divided by 3, or I can say 15 multiplied by 1 over 3. That's just the game we're playing here. And now I've got the other thing I need. All you require now is an example, as well as remembering that equation. And any other variation of that just follows the same little trick. You don't have to write in this middle piece. All I'm showing you is that it's just a version of the chain rule. It's a multiplying by 1. We already know that when y is a function of x, we can say dy dx is equal to the d dx at f at x. Mathematicians like to be efficient, to put down a very small amount of symbols and allow them move very quickly. The further on you move in mathematics, you find out that you're developing a new shorthand, and one of the versions of the shorthand in here is, rather than writing all of this stuff, it'd be very handy if we could say, well, isn't that can be called f dashed at x, and we'll only use f dash at x to mean this thing here. Also, if I differentiate it a second time, I'm going to differentiate the dash function now. That's the same as getting the d dx of the d dx of the original function. It can be written as t d2 dx squared. Now again, while we can understand it, that's getting complicated. It would be much easier to write this similarly. We stop at the third one because you don't pass the third one for the Leaving Cert, and you will be probably surprised to find out that we stop this shorthand method on the third one. This is a new one once you get into the fourth one. But for you in the Leaving Cert, you can actually see that it makes sense to write this instead of this long thing here. Now let's look at differentiating inverse trigonometric functions. This is, I admit, one of my pet little parts of the section. I know my handwriting is bad, but that was a little too bad. And you've come across your inverse trigs naturally in trigonometry, but how do we deal with them? How do we differentiate them? For example, what's the d dx of inverse sine x? What we need to understand is if y is equal to the inverse sine of x, what we are saying here in a nice roundabout way is something a lot simpler, that the sine of y is x. Okay? So inverse trigs are not a big scary thing. They're just, instead of looking down one side of a street, you're up the other side of it looking down the same street. It's just a different way of looking at the same thing. Now then, what would this guy be? It turns out to be this. How does that happen? Let's examine it. We're saying y is inverse sine. What if we went along and said sine y, we know, is x. That's just using this bit over here. Differentiate it. And clearly dx divided by dx is just 1. So we're saying the d dx of sine y. We don't know over here how this y function is working with respect to the x. So we'll say, use our chain rule again on it, and we can say it's cos of y dy dx is equal to 1. And from that we can say that implies dy dx equals 1 over cos y. That's all nice, easily done. We haven't an idea what cos y is though, so we have to go hunting for it. And what we do is naturally set up a right angle triangle, and we're going to appeal to our Pythagoras. It's a very particular right angle triangle because it's the one that belongs to the unit circle. There is technically, and you can imagine a circle going around like that, and there's your x-axis. That's 1. This will be 0. This distance here is cos, if that's theta, cos theta. That one is sine. That's all we're working on. Now we just have to apply that on a general principle. We can set y up any way we like. You can set it up in here. Sine of y. Okay. The sine is the opposite over the hypotenuse. And we know sine of y is x, which is x over 1. So that's x, that's 1. Now we want to work out this guy. That length here. You can call it L. We can say L is going to be the square root of 1 minus x squared by Pythagoras. See? That's how it's worked. Down here, we've worked this guy out. You will find in the logbooks just 3 of them: the sine, the cos, the tan. You will not find the sec, the cosec, and the cot. So you need to learn off the differentiation of those 3 inverses. Okay? We've arrived at the end of the first chapter in differentiation. It is an unusual chapter. It's a bit like the vectors chapter. It starts off complicated and a little bit difficult to manage, and then as you progress through it actually gets easier and easier. This chapter, the first chapter of differentiation, is actually more complicated than the second chapter. So you can look forward to the next talk where you can expect that the mathematics of this simplifies down. And the bit that seems to catch people, the bit about, find the maxes and find the mins, and then there's saddle points, which are horizontal points of inflection and all that kind of stuff. Generally the equations you're given when you're working that kind of thing are straightforward. You'll get a lot more complicated equations in this, the first chapter. And that's obviously the first question of the 2 differential questions in the paper. But even though they're more complicated, the whole trick, and really it's one of the great keys that mathematics gives us in our lives, the whole trick is, it may be complicated, it can always be broken down into simple problems. It's hard to conceive how useful multiplying by 1 is, and you've even seen an example of adding 0. And these are very useful methods to allow us start with something that's complex, and you systematically break it into smaller bits, and you can solve amazing problems. Well, I hope you don't forget the very basic concept of, when you're dealing with really complicated functions, of recognizing that they're in shells, a bit like an onion has layers. And you only can differentiate 1 layer in. Whatever is 1 layer in, you could differentiate that bit. But now, because the chain, you have the power of the chain rule, that layer now you look 1 layer in and you can deal with that, and you can keep going in until you get down to a situation where the variable you're differentiating with is only hidden by 1 layer, and then you're finished. This these problems here, inverse trigs, are straightforward. They like to ask you some complicated ones. You would think they're complicated. They've come up in the Leaving Cert, but there is a trick. And when you understand the trick, which we will go through when we're going through the past questions, you will find that none of the inverse trigs finish up any harder than what you're looking at here. So that's a promise I'll make to you, okay? That even the ones that you imagine are much harder won't be any harder than this. There's half of a part A in a Leaving Cert question which is like this one. There is a whole part C which has to do with an inverse trig, and the interesting thing is you can convert it into something as simple as half of a part A. So that's something to look forward to. Well, see you the next day when we will finish differentiation. At that point you will have covered all the sections necessary to allow us then move on to the special question. You have looked at series and sequences, you've looked at limits in relation to that chapter, and there's a little bit at the start here. You have your differential calculus, you'll have your integral calculus, you will have the binomial, which gives you very good insight into power series expansion and will allow you to understand how the Maclaurin expansion works, and you will find that the special question becomes very manageable for you. So okay, see you the next day.